Hello, in this video, we will introduce tail recursion. Tail recursion is efficient. We're going to look at why it is efficient in this video. First, what is a tail recursion? Tail recursion is this: when you have this recursive function, if you call the recursive function, when this recursive function returns, there's no pending operation in the function. So that means when this function returns, the entire recursive function is finished. So this one here in this function A is a tail recursion because this is the last element in the call. However, this in function B, when you invoke function B recursively in the middle, after this function B returns, you still have pending operations to finish. So this is not a tail recursion. The is palindrome problem, we have this recursive palindrome function. That palindrome recursive function is a tail recursion because when it returns true or false, that is over. The factorial function is not a tail recursion. So see, this is the factorial function. When it returns, you have to do n times the result from this return. So it's not a tail recursion. But we can modify the program to make it a tail recursion. So what we're going to do is write in this code here. So we're going to have this factorial helper. So here, factorial n invokes factorial helper n1. So what is this one here? It's the result. See, what is this? If n is 0, return result. Otherwise, we can return factorial helper n minus 1, and here is n times result. So what happens here, if this n is, let's say it's 5. So you're going to have 5 times 1 first. And the next time here, you're going to have 4 times 5. And then you have 3 times whatever the result is. And the 2 times result, 1 time result. In the end here, there's a 0 times result. That result is accumulating. It's the all these numbers multiplied together. So let's see why it is efficient. The reason it's because compiler can optimize the tail recursion. So when you invoke your recursive function, tail recursive function, and the call stack is not going to continue to grow because, you know, when you return it, you don't have to go back to the caller. It's just the entire recursive program is finished. So let's see it from this animation now.
The program loads the definition for the main function to the memory. The program loads the definition for the factorial function to the memory. The program loads the definition for the factorial helper function to the memory. The program invokes the main function. The main function is invoked and pushed to the stack. The statement displays a message to prompt the user for input.
Let's enter 3.
The statements prompt the user for an input. Read an input 3 from the console and assign it to variable n. The program invokes factorial n.
So now let's invoke factorial n here.
3 is invoked and pushed to the stack. The value of n in the main function is passed to factorial.
Factorial 3 is now on the top of the stack.
The program invokes factorial helper n1. Factorial helper 3(1) is invoked and pushed to the stack.
N is 3, result is 1. Factorial helper 3(1) is now pushed on the top of the stack.
The statement tests if n is equal to 0. It is false since n is 3. The program invokes factorial helper n-1, n times result. Factorial helper 2, 3 is invoked. Since factorial helper n result is tail recursive, the compiler does not create an activation record for this call. It will use the activation record on the stack.
So you see that for this function call here on the stack, when this is recursively called, you don't have to add another activation record on top of it because you can just reuse the previous space here. The reason is because this is tail recursion. Once it's finished, you don't have to go back to the caller. So you just go back to all the way to this factorial 3. So let's look at.
The statement tests if n is equal to 0. It is false since n is 2. The program invokes factorial helper n-1, n times result. Factorial helper 1, 6 is invoked. Since factorial helper n result is tail recursive, the compiler does not create an activation record for this call. It will use the activation record on the stack. The statement tests if n is equal to 0. It is false since n is 1. The program invokes factorial helper n-1, n times result.
Now n is 1, so n-1 be 0, and this n is 1, so 1 times the result is 6.
Factorial helper 0, 6 is invoked. Since factorial helper n result is tail recursive, the compiler does not create an activation record for this call. It will use the activation record on the stack. The statement tests if n is equal to 0. It is true since n is 0.
Now this n is 0 now, we're going to return result. Return result is completely finish the recursive function call. Return back to the caller, it's this factorial n.
The statement returns result. Since the function is tail recursive, this return statement will exit factorial n result function. Factorial helper 3, 1 returns 6 and it is removed from the stack. Factorial 3 is on the top of the stack. The statement returns 6 from factorial 3. Factorial 3 returns 6 and it is removed from the stack. The main function is on the top of the stack.
So this is the print statement now.
The statement displays the result.
And this is the last statement in the main function. The main function is now also finished.
The main function is finished and removed from the stack.
So
The program
that
adds
is
the definition for the main function to the memory.
all for this section on tail recursion. Through this animation, you see how tail recursion is called and why tail recursion is efficient. It does not grow the stack space as function is being recursively called. Because when the function returns, the entire recursive call is finished. That is all for this video. Thank you for watching. See you on the next video.